Okay, guys, video number 2. Again, if you are returning for this video, you have the benefit of seeing some really unique examples in here that can help you for sure in your homework or on your assessment. So here we have write equations for functions in standard form that have the following roots. So that means that we need to first write this in factored form, and then we need to proceed. Now it says write equations that have the following roots. Like, this could be interpreted just because it has roots at positive 5, positive 3, and negative 6. We don't actually know the order of these. So like if this was on a test, I would say write an equation for the degree 3 polynomial with the following roots, and that would confirm that these are order 1 factors. We are going to assume that these are order 1 factors just for the purpose of this. So f at x is equal to, if we have a solution at positive 5, then we have a factor at x minus 5. Positive 3 is x minus 3, and negative 6 is x plus 6. We have written an equation and again, it's a potential, it's a possible equation. We can't say for certain because we don't know what the a value is, but the thing here is this is asking in standard form, so that's where we have to distribute. So different ways, you guys might have learned it, the FOIL method, the rainbow method, but the best way to do it is to look at just 2 binomials first and say, okay, I'm going to do my first outside, inside, last. So I've got x times x, which is x squared. Okay, that's that times that. Then I've got x times negative 3, which is negative 3x. Then I have negative 5 times x, which is negative 5x. And then I have negative 5 times negative 3, which is positive 15. And this is all going to have to be multiplied by x plus 6. So let's clean this up a bit. X squared, negative 3x minus 5x is negative 8x plus 15. And this has to be multiplied by x plus 6. So then it's just annoying work. It's tedious, right? But we can do it. So the first term needs to be multiplied with both of these terms of the binomial. So we're going to have x times x squared and x squared times 6. So x squared times x is x cubed. X squared times 6 is, or times positive 6 is positive 6x squared. Then we're going to do the same thing with the negative 8x. So negative 8x times positive x squared is times positive x is negative 8x squared. Negative 8x times positive 6. Negative times a positive is a negative. 8 times 6 is 48. And we have that x in there. And then we have 15 times x, which is positive 15x. And we have 15 times 6. So if you think just mental math, 15 times 3 would be 45. And then times 2 is 90. So we have positive 90. And then we're almost there, but we just have to collect our like terms. So we have x cubed, where we had 6x squareds, but we took away 8 of them, so we're down 2 x squareds. We were down 48x, but we add 15, so if we add 10, that brings us to negative 38, and if we add 5 more, it brings us to negative 33x plus 90. Okay, so we haven't really reviewed expanding, but to write an equation in standard form is to do the opposite of factoring, that is to expand a factored form equation. Okay, so this here would be our final answer. F at x is equal to this. That's pretty standard. That's like serious review back to grade 10. This here, maybe not. So write a polynomial. So this would be a degree 2 polynomial. So write an equation for this polynomial in standard form. Well, method is still the same. We still have to start out in factored form. The problem here is these are the solutions. Okay, so remember that if, for example, just off to the side, if the solution is positive 2, then the factor is x minus 2. Okay, this is positive 1 plus, okay, so there's 2 solutions here. And clearly this is a this is a quadratic that's been factored using the quadratic formula, so we're probably dealing with non-integer solutions here. So we have a solution at 1 plus root 3, and we have a solution at 1 minus root 3. So if we had a solution at 2, we would write it as x minus 2. So we're going to do the exact same thing here. We're going to write it as x minus 1 plus root 3. 1 plus root 3 is just a number. It's just not a pretty one, right? And we're going to do the same thing here. X minus. I'm making them both minus because the coefficient is positive. Just like here, if it's positive 2, it becomes a minus. If it was negative 2, then we would write it as x plus 2. So because this is the positive, that's why I'm writing the minus there, minus 1 minus root 3. Okay, I have written this in factored form so far. That is no good because we want standard form. How are we going to convert this to standard form? In the exact same way. We're just using algebra. We're going to clean this up. First thing we're going to do is distribute this negative in both factors so that we can get rid of the brackets inside the brackets. So we're going to have x minus 1 minus root 3 over here. And over here we're going to have x minus 1 plus root 3. Okay, so still we're getting closer, but we do not have this in standard form. So now what we need to do, and what I recommend, is you do not combine these numbers because you're going to get some crazy decimals, and you will see what happens when we leave them just as they are. We are going to multiply, expand, first term, second, third, so forth. So I need to do x times x here, which is x squared. Then I have x times negative 1, which is minus x. And then I have x times the square root of 3, and we're just going to leave that. It's a positive, so as the positive root 3x. Then I have x, sorry, not x, now I'm moving on. Now I have negative 1 times x, so that's negative x. I have negative 1 times negative 1, which is positive 1. And I have negative 1 times positive root 3, which is negative root 3. And then I got to multiply this last term here. I have negative root 3 times x, which is negative root 3x. And then I have negative root 3 times negative 1, which is just positive root 3. And then I have negative root 3 times positive root 3. So I've got a negative times a positive, which is negative. Square root of 3 times the square root of 3 is just 3. Okay, just to use like a simpler example, square root of 4 times the square root of 4. We know square root of 4 is 2, and we know the square root of 4 is 2, and 2 times 2 is 4. So it always works out that way, that essentially the answer is just you drop the square roots and whatever's under the square root. So square root of 3 times square root of 3 is just 3. Okay, so now I can actually clean this up and something really neat happens. I had a positive root 3x, and over here I have a negative root 3x, so those cancel out. I had a negative root 3, and over here I have a positive root 3, so those cancel out. So now I'm just left with some really nice terms that I can collect. I've got still only one x squared. I had negative x minus x, which is negative 2x. And then I had positive 3 minus 2, which is negative 2. And there is my answer. I have a polynomial that has these solutions, and I've written it in standard form. And I can check my work. I actually already put this in Desmos to show you guys. So x squared minus 2x minus 2, x squared minus 2x minus 2. And we want to check, does this in fact have solutions at 1 minus root 3 and at 1 plus root 3. So those are our values. Remember, Desmos is just a graphing calculator, so I can put anything I want. So I'm looking for a solution at negative 0.732 and at positive 2.732. And when I click anywhere on my curve, I get those solutions at negative 0.732 and at positive 2.732. So that's perfect. Okay, so that's one thing you might come across where we're dealing with the equations, the solutions, the factors, just a different context of the question. All right, solve the following. 4x to the power 4 minus 24x squared plus 36. So then draw a sketch of this function. So this one's really interesting. You may come across something. You're like, well, if it wasn't x to the power 4, if that was x squared, if this was 4x squared minus 24x plus 36, I think I could use perfect square trinomial because 36 is a perfect square, which is 6, and 4 is a perfect square, which is 2, and 2 times 6 is 12, times 2 is 24. This is a perfect square trinomial, try 1, 2, 3, but it's a degree 4. So we're going to do a little substitution. We're going to say, okay, well then let's just call x squared n. And so instead of x to the power 4, if we had to make that in terms of n, it would be n being x squared. We would need to square it to get back x to the power of 4. So we need to square n. So we could rewrite this as 4n squared. We're replacing x squared. Anywhere we see x squared, we're replacing with n. So minus 24n plus 36 equals 0. And we could go through our factor theorem, integral zero theorem. We could go through it all, but this is so much faster. So now I'm like, oh yeah, I know how to factor this. Square root of the first, square root of the third. Square root of the first is 2. Square root of the third is 6. Sorry, I should say 2n. I've already checked that this is in fact a perfect square because, again, the square root of 36 is 6. I should say the square root. And the square root of 4n squared is 2n. 2n times 6 is 12n times 2 is 24n. So it meets all the criteria. And then just to recall how we factor a perfect square, we take the square root of the first, we take the square root of the third, and the sign is the sign between the first and second terms, and this is now squared. We could expand this if you didn't believe me, but now what we can do is resubstitute back in. So now sub x squared equals n in. So now we have 2 x squared minus 6 squared is equal to 0. So to solve this, remember that this square just tells us the order, but this square is different. We want to know if whatever is in this bracket becomes 0, the whole function becomes 0. So we need to say, okay, when is 2x squared minus 6 equal to 0? Inside the brackets, when the factor is equal to 0. So we use opposite operations. We get, okay, well, 2x squared is equal to positive 6. And then we divide by 2 on both sides, and we get, okay, well, what about when is x squared equal to 3? And we need to go one step further and get x by itself. And x squared is equal to 3. When we bring that squared to the other side, it's plus or minus the square root of 3. And again, just to show you with numbers that we're more comfortable with, if we said, well, when is x squared equal to 16? And we know that we use inverse operations to isolate a variable. So we can't just say that x is equal to the square root of 16, which is x is equal to 4. That does work if we subbed it back in. If we said, okay, well, 4 squared, yeah, that equals 16. But negative 4 squared is also equal to 16. So what we know when we're squaring is that whether it's a positive, 3 times 3 is 9, negative 3 times negative 3 is also positive 9. So when we rearrange to isolate our variable, in other words, to remove that square, we have to consider that the actual solution is plus or minus the square root of that number. So over here, then therefore x is equal to plus or minus the square root of 16, which in this case would be plus or minus 4. X could be positive 4 or x could be negative 4. Either one of those is going to fulfill x squared equals 16. So when we're looking at this example, we're going to leave root 3 as root 3 because it's not a pretty number like the square root of 16. It's not an integer, we'll call it, or a natural or whole. It's a rational number. So we will just leave it as x equals plus or minus the root 3. But that means, therefore, two solutions at x equals the square root of 3 and x equals negative the square root of 3. I should have wrote those in reverse order. So this question, if we go back up, said solve, then draw a sketch of this function. So what we know is that both of these are solutions for this factor that came from inside this bracket. That means that these are both order 2 solutions. The behavior of the function at both of these solutions are order 2. This is important if we want to sketch this function because the square root of 3, and we could go back over here. We can shove anything we want. We could say, okay, what's the square root of 3? Is 1.73. So we have a solution at positive 1.73. We have a solution at negative 1.73, and those are both order 2 solutions. We have a degree 4 polynomial with a positive leading coefficient, so it ends pointing up, and it also has the same end behavior on the other side. So this is a function that comes down, touches at negative 1.73 or negative root 3, goes back up. This graph is cut off just because of my screenshot. Comes back down, and again touches that positive and goes back up. Okay, obviously it's going to be connected. Okay, so there's 2 more kind of unique examples. This idea of recognizing, like, can I make this easier on myself? Is there any substitution I can do that can turn this into a quadratic? Because I'm really good at factoring quadratics, and then I can sub back in to deal with the solution from there. All right, another unique example is if we have a sum or difference of cubes. This is a perfect cube. I can take the cube root of x cubed and get x, and I can take the cube root of 27 and I get 3. 3 times 3 times 3 is 27. And now we don't need to check if it's a difference because now we have rules for difference or sum. So this is a sum of cubes. So I'm going to use my methods for factoring a sum of cubes. So if you remember, let's go back down here. The first factor is the cube root of the first term, which is just x. The sign stays the same as what we had. The second value is the cube root of the third, which is that 3. Then I take this number and I square it, or this value, whatever it is. So I have x squared. Then the sign is opposite. If this is plus, this is minus. Then I have these 2 terms multiplied together. This sign is always positive. And then I square this term. 3 squared is 9. I have now very quickly factored this function. And if I want to know when this is equal to 0, here's a little trick for you. It's equal to 0 when x is equal to negative 3, and only when x is equal to negative 3. Okay, then sketch. How do I know that? 2 ways. Number 1, this is a simple trinomial. A is 1. There are no 2 numbers that add to 3 and multiply to 9. The only numbers that multiply to 9 are 1 times 9. I can't combine a 1 and a 9 to get a 3. And 3 times 3. I can't combine a 3 and a 3 to get a 3. So this would be a quadratic formula question. But remember, when we're using the quadratic formula, we always check the discriminant. B squared minus 4ac. So b squared is negative 3 times negative 3, which is 9, minus 4 times 1, okay, a, which is 4, times c, which is 9, which is 36. That's going to give me a value that is less than 0. This, when we're dealing with the quadratic formula, this is the part that's under the square root. We cannot take the square root of a negative number. So if the discriminant, if the part under the square root is going to be less than 0, we can say, therefore, not factorable, or no solutions is really not factorable, no solutions. This is a quick way to check, but also will be the case every single time you're dealing with a sum or difference of cubes. And if you're wondering why, consider that this here is a parent cubic function that has one single transformation applied to it. So what transformation is that? That is a vertical shift up by 27. So I'm going to botch this because we know how sketching goes. But our parent cubic function, that's our function that goes like doot and keeps going. This here is just that function, but shifted up, way, way up. So now that little whoop is happening at 27. Because it's an odd degree polynomial, it has to cross the x-axis still, and that location is now no longer at 0. It is now happening at, in this case, x equals negative 3. And again, we could go back over to Desmos and say, okay, well, let's see what happens when we have x to the power of 3 plus 27. The whole function just shifts up. So we can get rid of these. We could zoom out if we want. there's that, and we could graph on the same Cartesian x to the power of 3. Okay, it's just the exact same function shifted up, and then what ends up happening is that x-intercept now changes. You can envision what would happen if we did minus 27. The whole thing just shifts down, and the y-intercept is now at negative 27. Okay, so there's another unique example. We've got a few things going on here. We looked at this. We looked at can we do some substitution to create a polynomial that we're more comfortable factoring? We looked at a sum of cubes and then sketching from there. And then this one is just use technology to solve the following polynomial function. And we've already been looking at this throughout the entire lesson, but we would just simply put the solution x cubed minus 6x plus 1. Okay, so x cubed minus 6x plus 1, we put it into Desmos graphing calculator, and we figure out our solutions as our x-intercepts. We would have one at negative 2.53, one at positive 0.167, and one at positive 2.361, we'll call it. I'm not going to write those out, but again, just recognizing that we can solve any polynomial, and that would be a polynomial that we're not obviously going to factor in this course. Those are some pretty funky intercepts, and so sometimes if that was the case. But the question would specify use technology if you needed to use technology. Okay, so now again, here are your practice questions. Oh, I should have mentioned this EOP just stands for every other problem. Basically what that means is this is a lot of practice. I'm not checking your homework. You're doing homework to strengthen your understanding. If question 1 is like A, B, C, D, E, F, G, H, I, if there's a million there, just do every other. Or just jump to the last two. Usually they get progressively more difficult. Do the last couple. If you've got them under control, then okay, move on to the next question. Okay? All right, I will see you back for lesson 6.